We're going to start chapter 13 today. It's on page 595, and it's about inference in linear models. So we studied in chapter 4 bivariate data, which is just ordered pairs when you have x and y's and they are related, or you are trying to see whether they are related or no. So usually what we did was we created some plots, scattered plots, to see whether the different points with coordinates x and y might follow a linear pattern. So the idea of this is that we want to find a linear equation that we're going to use to predict the values for y. So in these cases, x is going to be called the explanatory variable, and y is going to be the response. So when you get your linear equation to model this data, you're going to have y hat. Now y hat is going to be the predicted response. So it's going to be based on an y-intercept b naught and plus b1, which is going to be the slope of the line, times the explanatory variable x. So we call this equation the least squares regression line. So we want more than that. We want to be sure, we want to have certainty about the values for the slope and the y-intercept. So by using statistical models, we can create a linear model. So this is going to be a linear model, and this is going to be for a population where you're going to have now the mean for y values with respect to x being a function of the y-intercept. Now is denoted, the y-intercept for the population of the ordered pairs is going to be beta naught plus beta 1, which is going to be the slope for the population of ordered pairs times the explanatory variable. So we're going to learn today how to find confidence interval for this coefficient of the explanatory variable, and also we're going to run some hypothesis tests to know whether actually we can apply the linear model to our data, because maybe there is no sufficient evidence to consider this data set as following a linear model. So that's what we're going to do today in our class or this week. So we're going to have a data set. We're going to have x and y's. So in R, we're going to use our the way that we collect or we indicate collections of data values. So we're going to use lowercase c, parentheses, then we're going to enter every value separated by commas, all the values. And also the same thing for y. Then we're going to use some formulas that are in your book. They are slightly different, but the result is going to be the same. So we're going to start computing the z-scores for x, for every value of x in our table, the z-scores for y. So if you remember the formulas, it's just the value minus the mean over the standard deviation of the data set. And in R, you just need to write zx equals parentheses x minus mean of x over standard deviation of x. So we're just writing this formula in our terms. So once you have the z-scores for x and y, we're going to be able to compute the linear correlation coefficient R, which is the sum of the products of the z-scores divided by n minus 1. So in R, it's going to be just R equals sum of zx times zy, and that is going to be divided by n minus 1. We did this when we worked some problems on bivariate data in chapter 4. So then once you have the least square regression line, once you have the linear correlation, then you want to find the least square regression line. So to do that, we need to compute both the slope and the y-intercept. So we're going to use the linear correlation coefficient, R, and if you multiply that coefficient by the standard deviation of y and divide that by the standard deviation of x, you're going to get the slope. That is going to be the point estimate for the slope. So V1 equals R times SD of Y divided by SD of X, standard deviation of Y, the standard deviation of X. And then you're going to use this formula to compute the y-intercept for our line or regression line, which is going to be just the mean of y minus the slope times the mean of x. So b0 or b0 is going to be mean of y minus b1 times the mean of x. So once you have that information, we're going to be able to build a confidence interval for the slope. So this is going to be a confidence interval for the slope beta 1. And we're going to use these quantities to do that. We need to compute the standard error of the slope, which is given by this formula. It's slightly different from the formulas that you have in your book because I prepared these formulas to simplify our work in R. So also we're going to need the residual standard deviation, which is computed by using the standard error of the slope, the standard deviation of x, and the size of the sample minus 1. And to compute the margin of error for our confidence interval, the margin of error, we're going to use the t-distribution, the student t-distribution, and we need alpha, remember, to have a confidence level for our confidence interval. So once you find the corresponding student t value, you're going to multiply that by the standard error of the slope, and then that is going to be the margin of error. So the slope minus the margin of error that, is going to give you the lower limit for the slope for the population regression line, and the estimate V1 plus the margin of error is going to give you the upper bound or upper limit for the slope of the population of the bivariate data. Also, we're going to conduct hypothesis tests for the slope and for the linear correlation coefficient for the population, which is rho. And the hypothesis test is the same. So you're going to compute your test statistic t, which is going to be v1, the slope, over the standard error of the slope, if you have this information. Sometimes you are not interested in getting the confidence interval for the slope. You just want to know whether you can use a linear model, so you can just go directly and compute this parameter, this test statistic, by using the linear correlation coefficient. So if you do this computation, which is the same as this, you're going to get the same value, but without going through these steps here. So you go directly from here, from your linear correlation coefficient, directly to compute the statistic, and then you just have your null, which is going to be that rho equals 0, so that means no linear correlation between x and y, and your alternative is going to be either is less than 0, is greater than 0, or different than 0, the three possible choices. And also, if you are testing the slope, you're going to have the same null. So it's going to be just beta 1 equal to 0, and the alternative is going to be beta 1 less than 0, greater than 0, or different than 0. So the test is the same for beta 1 and rho. The result is going to be the same. If you reject the null for the linear correlation coefficient, you reject the null for the slope. So it's going to be the same. So if you test beta 1, it's like testing rho. If you test rho, it's like testing beta 1. So, and that's the reason I'm giving you the two formulas, because sometimes you want to test rho, you don't need to compute anything about the slope. You don't need to compute this section if you want to test only rho. If you want to test beta 1, which is the slope, then you need this section. So it's going to depend on the problem that you're going to solve. And once you have your test statistic, you're going to use either the critical value method or the p-value method to reject or not reject your null. Remember, if you reject the null, then that means that there is linear uh, correlation between X and Y. So you can use the linear model. So to use a linear model, to use the least square regression line, you have to obtain a decision that rejects the null. Otherwise, if you cannot reject the null, then you are not able to use the linear model. You can just use the mean of the y's as the way for you to predict the response. So that's a summary of the many tables and formulas that you have in section 13.1. So we're going to start solving some problems. We're going to just apply this formula. So we're going to start then formally section 13.1, which is on page 596, and the title of this section is Inference on the slope of the regression line. So that's section 13.1. So let's see. We're gonna have the first problem that we're gonna solve is problem is example. Let's see, example 13.1. So we're gonna solve example 13.1 on page 597. So let's read that example. So the example says the following. We're gonna use technology to find the least square regression line for the data in table 13.1. So table 13.1 is here, is about a data set based on nutritional analysis of more than 700 candy products conducted by the United States Department of Agriculture. So table 13.1 presents the number of calories and the number of grams of fat per 100 grams of product for a sample of 18 candy products. So we have here the values for X, so that's the explanatory variable, and the values for Y, those are the responses. So we are trying to explain calories by grams or fat. Okay. So this is my response. So if I have any quantity, any amount of grams of fat, what is the expected number of calories that is going to be obtained by consuming that candy? So I have values for X, values for Y. So in this case, my values for X are in this column and also in this column. The values for Y start here in this column and continue on this column. So be careful because order matters. So if you write 12.75 for the first value for X, when you write Y, the first value for Y should be 436. See, because these values are connected in some way. Y with the product. So we have here the different brands for candies and the results of the experiment. So we're gonna use R to enter our data and to compute the correlation coefficient first, and then we're gonna need to find the values for B0 and B1. So this is what we're gonna do now. We're gonna enter our data set again by using this way. We're gonna compute the z-scores, then we're gonna compute the linear correlation coefficient, and linear correlation, we're gonna be able to compute the least squares regression line, which is the purpose of this example. So we're gonna end up here. So that's what we're gonna do now. So I'm going to move to our console. So let's see. So we're gonna have to move and find our console, which is over here. So we're gonna start entering the values for the table. So I'm going to enter those values here. So I have here values for X from my table, values for Y for that table. You can press enter after any value on the command. You can continue on the next line. R is going to give you a plus sign indicating that you continue writing your data set. So you don't need to go until the end of the line. You can enter some, you can break the line in some sense to make more readable your data set. Then we're gonna enter the value for n, which is the number of data values in the data set. So let's see. So to do that, we're gonna have the following. So I'm entering n equals 18 because I have 18 data of order pairs. Then this is the formula to compute the z-score for X, the z-score for Y, then the formula for R, the correlation coefficient, then B1 and B0 are, so let's start with R. So R is going to be, I'm going to write that. So R is 0.96, 42,676. Then I'm going to find the slope is 5.63, 93.41, and finally the y-intercept is going to be 356.73, 92. So that's the results from the from this program. So let's check now. Let's compare with the values that are in our textbook. So I'm just going to copy what I got from R here. So so let's see. In your book, they used the Texas Instrument 84 to conduct this problem, to solve this problem. So they found the correlation coefficient. Here you can see the correlation coefficient 0.96, 42.6, and we have 0.96, 42.6. So it's the same correlation coefficient. Then V1 here is just B in this display for the Texas Instrument is 5.6393. In our console, we found 563.9341, and finally A here is the y-intercept 356.73. In our case, is B0 equals 356.7392. So that's the first problem. So we're gonna write then the least squares regression line is just y hat equals b0 plus b1x. So you're gonna write y hat equals 356.73 in 92 plus 5.63 93.41 x. So this is the equation of the line that is gonna model our data set. So now we're gonna solve another problem. So we're gonna solve problem. We're gonna solve example 13.3 and example 13.4 at once because they're gonna be about the same things. So I'm going to write here example 13.3 on page 600, and I also have example 13.4 on page 601. So let's read about those problems. So example 13.3, you can see here, is just we're going to need to compute the residual standard deviation for the data in table 13.1. So use the table that we just entered before in R. So the book suggests a lot of computations that you can see in this table. So you need to use the model that we just found, the linear, the equation of the line that we found, and you need to compute all the predicted values for the response, or all the predicted y's. Then you subtract the predicted value and the observed value, the response that you observe from the experiment. And then you need to do more things. You need to take the squares, and the sum is going to be part of the problem. And you need to use this formula over here to find the residual standard deviation. So it's a lot of work if you do this by hand. So we're going to use R again, and we're going to use the formula that I gave you before. So now this problem is asking us to find the residual standard deviation, SE. We're going to use this formula, but to find this residual standard deviation, we need to find first the standard error of the slope, which is this other formula. So we're going to essentially to apply these two formulas. I'm going to write them down now for you to see. So for problem 13.3, we're going to use the residual standard deviation is going to be SB times the standard deviation of x times the square root of n minus 1. But we need to compute SB, and SB is going to be the solution of the next example. That's the reason we are solving two examples at once. So example 13.4 is going to be about computing the standard error SB for the data in the same table. So now, for example, 13.4, we need SB, and SB is again another long computation. So we're going to need to conduct all these computations here. But in our case, we're going to use just a very simple formula that we have that I showed you before. So the formula is just SV is going to be the standard deviation of y over the standard deviation of x, and we're going to multiply this by 1 minus the square of the linear correlation coefficient over the degrees of freedom, in this case n minus 2. So this is standard deviation of x. So we're going to use R to find these two values at once. So let's move on to our console. So let's see. So we have now examples 13.3 and 13.4 that we're going to solve in one single step. So I have here the formula for the standard error of the slope and the formula for the residual standard deviation. So if I call SB, no, I need to call first, SE, because we are computing for example 13.3, we are computing the residual standard deviation. So we find that SE is 14.57 for 55, and for the other example 13.4 we need to call SB, so that is 0.3873 for 91. So that's the solution for these two problems at once. So I'm writing here the solutions. So now we're gonna check just our answers. So let's see. So for example 13.3, they find that the standard, the residual standard deviation is 14.57, and we got 14.57 here, and for the standard error of the slope, so they are finding here at the end of the computations 0.387349. So I'm showing you this just for you to be sure that we are getting the same answers, even though we're using the formulas that are slightly different. I just modify the formulas for you to be able to use R in a very, very simple way. So now we're going to work another example. We're going to work example 13.5. So let's see. Let me just go back here. So I'm going to write now example 13.5 on page 602. So now this example is going to be about constructing a confidence interval. So to construct a confidence interval, so we're going to construct a 95% confidence interval for the slope beta 1 for the candidate data. So we're going to use the same table. So you have here in your book the steps to build the confidence interval. So and you can see here that we're going to need the residual standard deviation, that we're going to need the standard error of the slope, and then we're going to find our critical value T alpha over 2 to be able to build the confidence interval, because we need to find the margin of error, and the margin of error is a function of the critical value that we're going to find. So here the margin of error is going to be T alpha over 2 times the standard error of the slope. So I gave you this information before, so it's over here. So this is the step that we're going to work now. So we need to find the margin of error for the confidence interval, and once you have that, then the margin of error is just the product of these two quantities. So we need alpha to compute the margin of error. So let's work on that now. So we need to find for a 95% confidence interval for the slope beta 1, the margin of error is T alpha over 2 times SB. So we're gonna have something like this. So these are our critical values. So this critical value here, T alpha over 2, is obtained if we know that this is alpha over 2 in both cases. So we have two critical values, but we only need one. So this critical value, if you remember, is obtained by using the function qt with 1 minus alpha over 2 comma, the degrees of freedom, n minus 2 in this case. Before we use only n minus 1 for degrees of freedom because we only had one data set. Now we have two data sets, then our degrees of freedom are going to be n minus 2. What are those two data sets? One is the data set for x, the other data set is for y. Actually, it's just one data set for ordered pairs, but it's like having two data sets, one for x and one for y. So let's find then the margin of error. So the margin of error is going to be just Qt of 1 minus alpha over 2, comma, n minus 2, and we're going to multiply this by SB. So let's do this computation. So it's going to be Qt of 1 minus an alpha. So if you have 95% of confidence, alpha is 0.05. You know this from previous exercises. So we're going to write here 1 minus 0.05 over 2, comma, we have 18 pairs, minus 2, and then we're going to multiply by SB, which is 0.3873491. So let me do this by using R. So let's move on to our R console. So to do this computation, so we have Qt of 1 minus 0.05 over 2, comma, n minus 2 times SB. It's already here. I can use just SB. So the margin of error is going to be 0.821143. So that's the margin of error for this problem. So then we need to add and subtract that margin of error from B1. So we have B1 minus 0.821143, and if we do that, we're gonna get 481, and then we're gonna add that value to get the upper limit. So my lower limit is gonna be 4.818198, and the upper limit is going to be 6.460484. So let me show you the notes, and then we're going to compare with the result that is in our book. So we have there the margin of error 0. So let me write here margin of error, the margin of error, the margin of error. So we can compare now our answer with the one that is in the book. So you have here so the margin of error here is indicated. You can see here that they found 0.82118 is slightly different from ours, and then the lower limit, the lower limit, then the upper limit. So essentially we got the same answer. So that's example 13.5. So let's continue with our work. I think we're gonna finish pretty soon, and then you're gonna have time to solve problems from the exercise set where you're gonna apply all of these things. So now we're gonna solve one more example. So the example that we're gonna solve now is, let me see. So we're gonna solve example 13.8. Okay. So let's see. We have example 13.8. Example 13.8 is on page 604. Now it's about hypothesis test. So this is a hypothesis test of the slope. And remember, any hypothesis test on the slope is going to be the same as on the correlation coefficient. So let's just read the problem is here. So for the data in table 13.1, the same table that we have been using, we're going to perform a test of the following. We have the null, which is just beta 1 equals 0 versus the alternative where we are expecting beta 1 to be greater than 0, and we're going to use the alpha level of significance equal 0.05. So that's the problem. So essentially we're gonna just write the null is beta 1 equals 0. The alternative is just beta 1 greater than 0, and this is equivalent. So you can write also that rho, the correlation coefficient for the population of the order pairs is going to be 0, and the alternative is that rho is going to be greater than 0. So in both cases, the null means no linear pattern, no linear model, no linear relationship. No linear relationship. That's the meaning of the null. So we need to reject the null to be able to use the linear model, either the least squares regression line or the linear model with the parameters with the interval, confidence interval for each one. So what is the next step? The next step is just we're gonna find our test statistic. So remember, we need alpha. Alpha is just going to be 0.05. Now our test statistic is going to be t, and t is going to be obtained by using either. So we provided two formulas. So you can use one or the other. So where are my formulas? So you have V1 over SV if you are following this column, or you can use directly R times the square root of n minus 2 over the square root of 1 minus R squared. So both can be used. So let's find our value for t. So you just need to go back to R, and we're gonna use the values that we already have. So either V1 over SV is the easiest one because we have all this information. So we are finding that our value for t is just 1455. I'm going to write that 1455 a1. So that's the value for the test statistic. So now we're gonna use, you can have either a critical value method or the p-value method. So let's start with the critical value method on this, and for the other case we're gonna use the p value method again, or you can use either. So for the critical value method, we have our t distribution, and this is a right tail test. As you can see here, this is a right tail test, a right tail test. So you're gonna look for a critical value here. So this is gonna be your t alpha, the one that you're gonna use to decide whether your test statistic, this one, is either inside of the region that favors the null or outside of that region. So let's find t alpha. T alpha is going to be just qt o 1 minus alpha and degrees of freedom. So in our case is qt1 minus alpha is even, is according to this problem is 0.05, so we're gonna have 0.05, n is 18 minus 2. So here my critical value, let's use r, finish this part. So we're gonna have here qt01 minus 0.05 comma 18 minus 2 degrees of freedom. So this is 1.74, 5884. So and with that we're gonna be able to make a decision about our test statistic. So 1.74. So this is this value here. So where is our test statistic here? If you plot this, so we're gonna see that it's gonna be in this region. So you're gonna reject the null. So that's the conclusion for this problem. So now I'm going to finish the other part with the p-value method, but before that I'm going to show you example 13.9 is for the data in table 13.1, which is the same. We're going to perform a test of with the null again, beta 1 equals 0 versus beta 1 greater than 0, again the same significant level, but they say that they're going to use technology, but the point of this example is that they are using, in this case, the p-value method. So it's the same thing that we are doing. We're going to continue our work. So this is, let's say, example 13.9 on page 605. So, and is the same as testing the correlation coefficient. So let's finish this. So for the p-value method, we need to have our test statistic here. So you have here t equals 1455a1, and we need to find this area. This is my p value. So what is this p value? This p value is going to be obtained by using 1 minus pt. Here we're going to use t and n minus 2 degrees of freedom. So let's find this p value by using r. So we go back to our console, and now we're gonna find 1 minus pt of t. T is just 14.55 a1, comma 18 minus 2 degrees of freedom. So we're gonna find a very small value, 5.972733 times 10 to the negative 11. So that's our p-value. So then the final step is that we're gonna compare you're gonna compare p-value and alpha. So you can see here that this is a very small number, so your p-value is less than alpha, much less. It's very small. So it's a strong support for your decision of rejecting the null. And when you reject the null, when you are working with a linear models, that means that you can use, so you can say that the order pairs are linearly correlated. So you can use a linear model like the one that we found before. So now it's going to be your turn to work on some problems, and you're going to tell me those problems by taking screenshots, and that is going to be all for today. So let me see where the problems are. So I have two problems for you. So, and with those two problems, you're gonna complete your classwork for this section. So these problems are from section 13.1, exercise set on page 609. So you're gonna work problems 20 and 22. So I'm going to show you now the problems. So please take screenshots if you don't have your book. So let me see. You have the following. So problem 20. So like father, like son. So you have just the height of a father and the height of his son. So one is going to be your x, the other one is going to be your y. So usually in this case your x is going to be the first column, and remember the column continues over here. So this is the data set for x, and this is the data set for y. Then you're going to answer these questions. You're going to compute the least square regression line. So just y hat equals v0 plus v1x. Then the next part is that you're going to construct a 95% confidence interval for the slope, something that we just did. And then you're going to conduct a hypothesis test where you are testing the slope being 0 or the linear correlation coefficient being 0. So that's the first problem. That's problem 20. Then a similar problem is going to be 22. It's about blood pressure. So you have again two columns. The first is x, y, and then x continues here, y continues here. So that's your data set. And again, you're going to compute the least square regression line. Then you're going to construct a 99% confidence interval. So pay attention to the, in this case is 99 confidence interval, and then another testing. So you're going to test the slope being 0. And check the confidence level in this case, the significant level, 0.01. So, and that's it. So solve these problems Send me your answers by using the classwork section on Canvas. Remember, you need to upload a file. Uh, I would like to have a PDF file if possible. And we're going to continue with the next chapter next week.